Welcome to CyberExplain channel. Today we are going to discuss AI model supply chain security, guarding the brains of tomorrow's tech. Hey everyone, welcome back. Today, we are diving headfirst into a topic that's quickly becoming one of the most critical frontiers in cybersecurity, AI model supply chain security and provenance. Think about it, AI models are increasingly making decisions that affect everything from our finances and healthcare to national defense. But how much do we truly trust these models? Are they doing what they're supposed to do, or have they been tampered with along the way? That's the core question we are tackling. We are moving beyond just securing the code. We are talking about the entire journey of an AI model, from inception to deployment. This isn't just theory, it's about protecting the very intelligence that powers our future. It's an advanced challenge, requiring sophisticated solutions. So, what exactly do we mean by the AI supply chain? It's vastly more complex than a traditional software supply chain. We are not just talking about source code and libraries anymore. We've got raw training data, feature engineering pipelines, pre-trained models, hyperparameter optimization, model architectures, weights, inference code, deployment environments, the list goes on. Each of these stages, each component, represents a potential attack vector. A malicious actor could inject poisoned data, modify model weights, or even swap out a legitimate model for a compromised one. It's like a manufacturing line where any station can be sabotaged, potentially leading to a flawed, dangerous final product without anyone noticing until it's too late. The stakes here are incredibly high. Imagine a compromised fraud detection model letting sophisticated scams slip through, or a medical diagnostic AI misidentifying critical conditions. We've already seen data poisoning attacks like the one researchers demonstrated against a facial recognition system, where subtle changes in training data led to misidentification. Or consider the potential for backdoors injected into foundational models used across industries. The reputational damage, financial loss, and even physical harm from such incidents could be catastrophic. Without robust security, the very trust we place in AI crumbles, hindering innovation and adoption. It's not just an IT problem, it's a business and societal imperative. Provenance, in simple terms, is the history of ownership and origin. For AI, it's about tracing every step a model took, from its initial concept to its current deployment. This isn't just good practice, it's absolutely fundamental. Unlike traditional software, where a static code base is often the primary artifact, an AI model is dynamically shaped by its data and training environment. Its code is constantly evolving through learning. We need to know where the data came from, who curated it, which algorithms were used, what hyperparameters were tuned, and who approved each change. Without this detailed lineage, any anomaly or poor performance becomes a frustrating, often unsolvable, mystery. It's about building an unshakable audit trail. You are probably familiar with the concept of a software bill of materials, or SBOM, for traditional applications. It lists all the open source and commercial components in a software product. But for AI, we need something far more comprehensive, a model SBOM. This isn't just about Python libraries, it details the entire AI artifact. Think of it as a nutritional label and an ingredient list combined, but for an AI model. It provides transparency into everything that went into building and training that model. This becomes our foundational document for understanding, auditing, and securing the model throughout its entire life cycle. It's our first line of defense in understanding what we are actually deploying. So, what specific details go into an AI model SBOM? It's a rich dataset. We need metadata like model name, version, and unique identifier. Crucially, we include the training data sources, their versions, and any preprocessing steps applied. Then there's the model architecture itself, the framework used, PyTorch, TensorFlow, specific library versions, and hyperparameter configurations. Don't forget the training code version, hardware used, and even metrics from training runs. Finally, it should detail any pre-trained components or transfer learning stages. This level of detail allows us to reconstruct, verify, and understand the model's entire developmental journey. It's a snapshot of its genetic makeup, if you will. Generating these comprehensive SBOMs isn't a manual task, it requires automation and integration into your MLOps pipelines. Tools like AIML, Kubeflow, or even custom scripts within your CI/CD can help. The key is to capture metadata at each significant stage: data ingestion, feature engineering, model training, and packaging. You want to integrate this generation as a mandatory step before any model can be registered or deployed. Think of it as an automated build manifest. This process ensures consistency, reduces human error, and creates a verifiable record that's much harder to tamper with after the fact. We are essentially baking in transparency from the very beginning. Let's walk through our scenario. We have a critical fraud detection model deployed in production. The first step in creating its SBOM is documenting its data lineage. Imagine this model was trained on historical transaction data. Our SBOM would list the specific S3 bucket path, the exact version or timestamp of the CSV files, and cryptographic hashes of that dataset. It would also detail the Python script with its git commit hash used for anonymization, feature engineering, and splitting. We'd track if any external datasets were merged, like publicly available IP reputation lists, again with their source and version. This meticulously documents the ingredients that shaped the model's understanding of fraud. Continuing with our fraud detection model, the SBOM now extends to the model artifacts themselves. We capture the specific TensorFlow or PyTorch version used, the exact Python package dependencies, like scikit-learn or numpy, all with their pinned versions, and the architecture of the neural network. We'd include the git commit ID of the training script, the hardware configuration, example, specific GPU type, where it was trained, and key training metrics like accuracy or F1 score. Even the specific Docker image ID used for packaging the model for deployment goes into this SBOM. This comprehensive artifact-level detail ensures that the model can be consistently reproduced and its exact configuration verified at any point. Even with an SBOM, adversaries can target it. A sophisticated attacker might try to tamper with the SBOM itself, altering crucial details like the recorded training data hash or dependencies to hide malicious injections. They could obfuscate components, making it difficult to verify their true nature, or introduce seemingly benign, but vulnerable, open-source libraries that contain hidden backdoors. Imagine an attacker changing the recorded version of a data preprocessing script in the SBOM to conceal one that actually injects bias or specific trigger patterns. This is a subtle yet powerful attack, undermining the very trust the SBOM is designed to build. The SBOM itself becomes a target. Detecting SBOM compromises requires vigilance. The most straightforward approach is cryptographic hashing. Every critical component listed in the SBOM, from the training data files to the model weights and inference code, should have its hash recorded. At deployment, or any audit point, recalculate these hashes and compare them against the SBOM. Any mismatch signals tampering. Furthermore, you can use anomaly detection on SBOM content itself. If a dependency suddenly changes from a stable version to an obscure, newly added one without a clear change management record, that's a red flag. Integrating SBOMs into a central logging and alerting system is key here, enabling automated checks. To mitigate these risks, we need to secure the SBOM itself. First, ensure that SBOMs are generated in a trusted, isolated environment with strict access controls. Use strong cryptographic signing for the SBOM file itself, so you can verify its authenticity and integrity. Store SBOMs in immutable, tamper-evident storage, like a blockchain-based ledger or a warn, write once, read many system, perhaps integrated with your model registry. This prevents retroactive modification. Implement strict approval workflows for any SBOM changes, and integrate SBOM generation directly into your automated, signed CI/CD pipelines. Treating the SBOM as a critical security artifact, not just documentation, is essential. While the SBOM gives us a static snapshot of a model's state at a particular point, provenance goes further. It's about recording the asterisk sequence of events asterisk that led to that state and how it evolves over time. This isn't just about what components are present, but asterisk how asterisk they came to be, asterisk who asterisk acted upon them, and asterisk when star. Think of it as a detailed transaction log for every significant operation in the model's life. This dynamic tracking is crucial for debugging, auditing for compliance, and forensic analysis after an incident. It provides the narrative behind the snapshot, telling the complete story of the model's journey and transformations. Let's zoom in on data provenance, because it's arguably the most critical aspect. Poor data provenance can lead to garbage in, garbage out problems that security and integrity checks downstream simply can't fix. We need to track the origin of raw data, every transformation applied, every filter, every anonymization step, and every person or automated process that touched it. This includes tracking data drift and concept drift over time. Imagine auditing a biased model. You need to trace back to the exact dataset version and transformation script that introduced the bias. Tools like Apache Atlas, OpenLineage, or even custom data catalog solutions with robust versioning can help build this chain of trust. It's about knowing if your foundational truths are indeed true. Model provenance is also intimately tied to robust versioning and lifecycle management. Every change to a model, a new training run, a hyperparameter tweak, a code update should result in a new, distinct version. This means not just model underscore v2, but something like model underscore v2.1.3 experiment A GPU. Each version should have an immutable record of its associated data, code, and configuration. MLOps platforms like MLO or Vertex AI provide excellent capabilities for this, allowing you to register different versions, track their metrics, and transition them through stages like staging to production. Without this granular versioning, understanding the impact of changes or rolling back to a known good state becomes impossible. It's essentially Git for your entire AI artifact. Let's revisit our fraud detection model. Suppose it suddenly starts exhibiting a peculiar bias, disproportionately flagging transactions from a specific geographic region. With robust provenance, we can immediately begin tracing its ancestry. We'd query our MLOps system to identify the exact model version deployed. From its SBOM and associated provenance logs, we'd identify the training data source, its version, and the preprocessing script used. We might find that a new geolocation lookup table was introduced in a particular data transformation step, or that a specific region's transaction data was underrepresented in that training dataset version. This granular traceback allows for rapid root cause analysis and targeted remediation, turning an opaque problem into a solvable one. Without it, you are flying blind. Adversaries can directly attack the provenance records themselves. They might attempt to forge or alter historical logs to obscure the introduction of malicious code or data. Imagine an insider with privileged access swapping out a clean data preprocessing script in the version control system with one that introduces a subtle backdoor, then modifying the provenance log to record the original script's hash. This is a form of history rewriting. Or, they might exploit vulnerabilities in your MLOps platform to inject false provenance entries, making a compromised model appear legitimate. The goal is to break the chain of trust, making it impossible to verify the true origin and evolution of a model. This is a very insidious attack. To counter provenance tampering, immutability is your best friend. Storing provenance records in a tamper-evident ledger, like a private blockchain or a system with append-only logs and cryptographic chaining, is a powerful defense. Each new provenance entry is cryptographically linked to the previous one, making any modification immediately detectable. Beyond that, Rigorous access control and integrity checks on your MLOps platform's database are crucial. Regularly auditing logs, looking for unusual activity or unapproved changes to configuration can also expose attempts. Consider a system where every commit to a data transformation script repository automatically triggers a signing event and an immutable log entry. This makes history rewriting incredibly difficult, if not impossible. Okay, so we've built our SBOMs and are tracking provenance. Where do we keep all these models and their metadata? That's where model registries come in. Think of them as your version-controlled, secure vault for all your trained AI models, their artifacts, and associated metadata. Platforms like AIML Model Registry, Azure Machine Learning Workspaces, or even Hugging Face Hub for pre-trained models provide this crucial functionality. They allow you to store different versions of models, manage their lifecycle stages, staging, production, and serve as the single source of truth for deployment. But remember, a central hub is also a central target. Securing this registry is paramount, as a compromise here could affect every model in your organization. Securing a model registry isn't just about passwords. It's about a defense-in-depth strategy. This means isolating the registry in its own network segment, applying strict firewall rules, and ensuring all communication is encrypted, TLS everywhere. Consider a multi-tiered architecture where public-facing APIs for model serving are strictly separated from the internal management APIs for model uploads and updates. Regularly scan the underlying infrastructure for vulnerabilities, including the database, storage, and container images used by the registry service. Treating your model registry like a critical data repository, which it absolutely is, means applying the same stringent network and infrastructure security controls you would for sensitive customer data. Beyond network security, robust identity and access management are non-negotiable. Implement strong authentication, ideally integrated with your enterprise identity provider like Entra ID or Okta using multi-factor authentication. Authorization needs to be granular. Who can *read *model metadata, who can *upload *new model versions, who can *transition *a model from staging to production, and who can *delete *a model. These should be distinct roles with the principle of least privilege strictly enforced. For example, a data scientist might have upload permissions to a staging environment, but only a release engineer can promote to production after a rigorous security review. Think about role-based access control, RBAC, down to the model level. Let's imagine securing our enterprise's Azure Machine Learning Model Registry. We'd start by assigning roles. Data scientists get contributor access to their specific workspace's model registry for uploading new versions and viewing details, but not for promoting to production. A dedicated MLOps engineer group has permissions to transition models to production status, but only after a pull request review of the model's SBOM and performance metrics. Crucially, the service principal used for automated deployments from the registry only has reader access to retrieve models and a separate model deploy role with just the permission to deploy, scoped strictly to production endpoints. All access is logged to Azure Monitor and fed into our CM for anomaly detection, ensuring every interaction is audited. The registry, being a central point, is ripe for specific attacks. Insider threats are a major concern. A disgruntled employee with legitimate access could upload a malicious model version or tamper with existing ones. External attackers, after gaining initial access, might use the registry for supply chain poisoning, injecting models with backdoors or adversarial vulnerabilities, hoping they'll be deployed unwittingly. Imagine a seemingly minor patch to a model, but that patch, uploaded to the registry by a compromised account, subtly alters the model's decision-making in specific edge cases. Or, an attacker could simply delete critical model versions, causing massive operational disruption. This makes robust authentication and continuous monitoring absolutely vital. To detect attacks against registries, extensive audit logging is non-negotiable. Every access, every upload, Every version transition, every deletion must be logged with user, timestamp, and action details. These logs need to be immutable and fed into ACM. Beyond simple logging, employee behavioral analytics. Is a user who normally only reads model metadata suddenly attempting to upload new versions to production? Is there an unusually high volume of model deletions? Are models being deployed from unexpected sources? These anomalies can be strong indicators of compromise. Automated alerts on critical actions, like a model being promoted to production without a specific set of security checks being recorded, are also essential. Timely detection is key to limiting blast radius. Once a model artifact, including its weights and inference code, has been created and its SBOM generated, how do we ensure it hasn't been tampered with after generation and before deployment? Cryptographic signatures are your answer. Just like you'd sign a software package, you should sign your compiled model artifacts and their associated SBOM. This involves using a trusted private key to generate a digital signature over the artifact's hash. Anyone can then use the corresponding public key to verify that the artifact originated from a trusted source and hasn't been modified. This provides cryptographic assurance of integrity and authenticity, guaranteeing that the model you are about to deploy is precisely the one you built and validated, not some malicious imposter. Signing is great for pre-deployment, but what about at runtime? We need continuous integrity checks. Before a model loads and begins inference, its cryptographic signature should be automatically verified against the artifact and its expected public key. If the signature is invalid or doesn't match, the model should simply refuse to load. Beyond that, consider runtime monitoring of model behavior for deviations from a baseline. Are the outputs suddenly very different? Is inference latency drastically longer? Are resources being consumed unusually? These could indicate a hijacked model, even if its static integrity checks passed. This belt and suspenders approach provides a robust last line of defense against both static tampering and dynamic compromise. Back to our fraud detector. After training, the MLOps pipeline cryptographically signs the final model weights, the inference script, and its SBOM using a dedicated, hardware-backed key management system, example, AWS KMS or Azure Key Vault. These signed artifacts are then pushed to the secured model registry. When our Kubernetes deployment controller pulls the model image, before it spins up the inference container, a pre-init container step automatically downloads the model, its signature, and the public key from a trusted source. It then runs a verification script. If the signature validates, the main inference container starts. If not, the deployment fails, triggering high-severity alerts. Furthermore, our monitoring continuously checks inference logs for suspicious patterns, like a sudden drop in flagged fraudulent transactions or an increase in false positives, catching behavioral compromises. While cryptographic integrity checks are vital, they don't protect against models that are designed to be malicious from the start. This falls into the realm of adversarial machine learning (AML). We are talking about data poisoning, where attackers subtly corrupt training data to inject backdoors or bias into the model. Or evasion attacks, where inputs are crafted to bypass a model's detection without triggering integrity alerts. These aren't about tampering with the model artifact they're about manipulating its learning process or its inputs. Defending against AML requires robust data validation, secure training environments, explainable AI, XAI, for understanding decisions, and adversarial training techniques. It's a whole new layer of sophistication in model security. Alright, we've covered a lot today. From understanding the extended attack surface of the AI supply chain to the nuances of model SBOMs, dynamic provenance tracking, securing registries, and verifying model integrity with cryptography and runtime checks. What's clear is that securing AI isn't a single silver bullet, it's a holistic, multi-layered approach. It requires integrating security from the very first byte of data collection all the way through to post-deployment monitoring. Trust in AI models isn't given, it's earned through diligent, continuous application of these advanced security principles. Our goal is to ensure that the AI systems we build and rely on are not only powerful and efficient but also inherently trustworthy. Keep learning, stay curious, and let's keep building a more secure AI future together. Thanks for watching. Subscribe to the CyberExplain channel. See you on the next video.